Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
How you doing today, guys?
I'm fine. Oh, sorry.
No, yeah, how you doing, Mrs. G?
I'm doing fine, thanks, Mr. Kane.
I feel like I'm having a conversation here. All right, today we are going to talk about something very boring.
Oh, Mr. Kane.
All right, so yeah, we're going to talk about the Bohr model of the hydrogen atom.
Okay.
A little bit of math here.
All right.
Not much more math than what we've done already, and it's pretty comprehensible.
Niels Bohr, yeah? Wasn't that his name?
Yeah, Neil. Niels? Neil?
Niels, I think.
Yep, German guy. I guess you pronounce the S.
I don't know. Continuous atomic spectra. Spectra from white light. White light gives off all wavelengths, frequencies, energies in a continuous stream of color.
Roy G. Biv.
Roy G. Biv.
Or
Equal abundance.
right. So you get all of these colors. This is a breakdown of the white light spectrum, right?
Yep.
So we've got something called a spectrometer, and we're going to get to use those spectrometers in class, right?
Yep.
And when we look at white light through the spectrometer, it basically breaks it down into a prism of colors, and you can actually measure the different colors. Like, say, if I wanted to know exactly what color this was right here, that line of lights, that kind of purple, I would say that it was about 400 nanometers.
So the white light kind of goes in a continuous stream, though, isn't it? Like 400, 401, 402. It's a continual.
Yeah. The very next line over here, the next line of purple, the next shade, if you will, is 401, then 402, and then this here would be 410 right there. And by the time we get to 420, you don't really call it purple anymore. You
Yeah,
now
it's starting to get in a blue.
It's starting to get blue. You get up to 440, it's dark blue.
Yeah.
I think 490 is like aquamarine.
Yeah.
You know,
So it's all of it.
this is 16 million colors.
Oof.
Or more.
Dang, that's a lot of colors.
Yeah, you can count those. All right. The reason why we showed you that is because white light gives off all the colors. It turns out that different atoms can be excited and caused to give off light themselves.
And it's very specific colors, isn't it?
Yeah, notice hydrogen doesn't give off a complete spectrum of Roy G. Biv.
Yeah, there's no yellow.
There's a red, there's a
Orange.
green, there's a blue, and there's two purples.
Wow.
Helium gives off a different spectrum. Neon's a different spectrum. So these are kind of like fingerprints of the atoms.
Okay, yeah, because they're all kind of different, aren't they, depending on what the element is?
Mm-hmm. And this is one of the ways that they know what the sun is made of.
Okay.
If you make atoms glow, they give off certain frequencies of lights, certain wavelengths.
These are colors coming out of an excited gas phase, right?
Right. It's coming out of an atom that's glowing,
Okay.
which are excited. Yeah.
So these are not continuous spectra, because if it was continuous spectra, it would look like the previous example.
These are emission spectra, because the atoms are emitting lights. Okay. All right. And obviously you could probably Google, if you wanted, all sorts of atoms. You could Google your favorite atom and find out what spectrum.
These are usually in the gas phase, because our tubes that we have are in the gas phase. So.
Usually, yeah.
Okay.
All right.
Only certain wavelengths, frequencies, energies, and colors are present.
And there are reasons for that.
Okay.
And Neil Bohr, the reason why we're talking about him today is because he's the one who figured out why there are certain frequencies, certain colors of lights.
Now, when you say colors are present, does that mean it's always in the visible spectra?
Colors is kind of in quotes here. It could be. Colors is kind of in quotes because it could be that the color could be ultraviolet.
Right, because there's some...
Or X-ray.
Oh, so you're using the
gamma.
word colors in exchange for light.
Yeah.
Okay.
A better word might be EM spectra.
Okay. Because I know there's like the Balmer series and stuff like that. That's in...
Yeah, that gets more in
Yeah,
depth.
that's UV, infrared kind of thing. Okay, so only certain wavelengths, frequencies, energies, and light are present. So it could be not necessarily in the visible range.
Right. It could be anything all the way from gamma rays down to radio waves. So because light is energy, each atom, according to Planck, is emitting quantized amounts of energy, certain amounts of energy.
And not continuous. Okay.
And not continuous. So if the atoms could emit any amount of energy, any atom would give off a continuous spectrum. So you'd see Roy G. Biv from hydrogen and Roy G. Biv from helium.
So hydrogen, not only is it not a continuous spectrum, but it only has allowed energies. So it can't give off one at 670. It's limited to 410 and that.
It's
Like
limited
that?
to very specific amounts,
Oh,
quantized amounts.
So that's what he was talking about.
Right.
They're very specific pieces of energy from each element.
Right, and Bohr's the one who figures out how to tell what specific energies.
Okay.
So Bohr's model of the atom says that electrons move in things called orbits,
Okay.
and it numbers the orbits 1, 2, 3, and Bohr says that we can have an infinite number of orbits in an atom.
Okay, so he hypothesized there's an infinite number.
Yep.
He also thought they were pretty nice concentric rings, too.
All right.
Atom is held together by Coulomb's law.
Right.
Opposites attract, because, of
Right.
course, an electron is negatively charged and the nucleus is positively charged, nuclear charge.
Right. And
Good.
he says that the energy of an electron increases as you get further from the nucleus, or the energy of the orbital increases the farther you get from the nucleus. So an electron in the second orbit has more energy than an electron in the first.
And less than the third.
Right.
Okay.
Okay. Another rule, electrons are most stable when closest to the nucleus.
So this one's really important because they are supposed to be in that first orbit. That first orbit is low energy, it's stable, and it's closest to the nucleus, right? And it is the lower energy level.
And it's called the ground state.
Ground state. Okay.
Okay, that's the normal state of the atom. The energy of each orbit is found by calculation. You can see here energy of n, which is energy of the orbital, is equal to negative 1,312 kilojoules per mole divided by
N squared.
n squared, the number of the orbit squared.
Okay.
All right, so here's our equation, right?
Right.
If we're going to do the energy of the first energy level, so E sub 1, all right, you do the math. Ms. G, are you really doing calculations on this one? What's 1 squared?
I'm doing the second one, Mr.
Oh, okay, all right. I'll do this one. Sorry, you are doing the second one. So 1 squared is 1, and negative 1312 kilojoules per mole divided by 1 is negative 1312 kilojoules per mole. So the energy of the first energy level is
Negative 1312 kilojoules per mole.
all right. The energy of the second energy level would be calculated by taking negative 1312 kilojoules per mole and dividing by 2 squared. Mrs. G, you've done this one already.
Yep, negative 328.
Kilojoules per mole.
Now, that's an increase because the negative signs are literally
We're getting closer to
value.
0.
Yep, getting
Yeah.
closer to 0.
All right. So the energy of the third energy level is negative 1312 kilojoules per mole divided by 3 squared.
Which is 146.
146
We're getting closer to 0.
kilojoules per mole. Hey, if we do this in an infinite number of times, I bet you we'll get closer to 0.
Well, let's see. Do number 4 for me.
Energy of the fourth. I predict that this is going to be even closer to 0 than the last one.
Okay.
1312 kilojoules per mole divided by 4 squared. Oopsie, that's not 4 squared. This is 4 squared.
82, negative 82.
Negative 82 kilojoules per mole.
All right.
Will we ever reach 0?
All right, let's try something, Mr. K. Now, Bohr said up to infinity. So what if, theoretically, there should be an orbit of 2,876?
2,876. Okay. So we're getting closer to infinity here. Negative 1312 kilojoules per mole divided by 2,876 squared.
Yep.
What do you get?
You get a negative 1.59 times 10 to the negative 4.
Wow.
So
And
points
that's kilojoules per mole.
So that's a negative 0.000159. So yeah, you keep getting closer and closer to 0.
Do we ever reach 0?
No, unless it's completely removed from the atom, that's 0 technically.
Is that why Bohr did that?
Yeah, that's why Bohr did that. He theorized that an electron completely removed, because of course you make ions, so you're removing electrons, so an electron completely removed from the atom has an energy of 0. We just calculated the energy levels of the first 4 orbits in the Bohr model,
Right.
and orbit number 2,900, whatever that one was.
2,786.
And we got negative values for every energy orbit. How come?
Well, the reason for it is that Bohr wanted a single electron, when you take a single electron away from an atom, he wanted the electron to have 0 joules of energy.
Okay, so an electron completely removed. All right.
So the only way to do that if you were to give an electron more energy by making it go up in their positive numbers, when you make an electron fly off an atom and completely be removed from it, the numbers keep getting higher and higher. So an electron would have an infinite amount of energy.
Okay, so he needed
the electron to have 0 energy.
All right, wait. Let me get my head wrapped around this. So an electron completely removed has 0, and he needs something to depict less than 0 when it's part of the atom.
Right. So that's why the numbers wind up being negative. That's why we wind up having negative energies for each of these orbitals.
These are literally negative values. These are literally less than 0 values.
All of them.
Woo.
Okay.
Good thing this is a theory.
And what that means is that the closer the electron is to the nucleus, the larger the negative value of the energy. So
which is the less energy, the smaller the energy.
As we saw, n equals 1 is going to have negative 1,312 kilojoules or so per mole. And it's going to get closer and closer to 0 as we go out.
Move away from the nucleus. Okay.
All right, so this is Bohr's conceptual model of the hydrogen atom. Again, what we're seeing is concentric circles that are orbits around the nucleus where the electrons live. The nucleus should be this dot right in the center of the atom. Of course, it's drawn much larger than it should be. Bohr's been able to calculate how much energy each of these energy levels contains. He says the first energy level contains negative 1,312 kilojoules per mole. Energy level 2 is negative 328 kilojoules per mole. Energy level 3 is negative 146 kilojoules per mole. And energy level 4 is negative 82 kilojoules per mole. He goes on to talk about how electrons can move from one energy level to the next. According to his model of the hydrogen atom, the atom basically looks like this. The one electron that's in it is in the lowest energy level. It's in the first energy level, meaning that it has negative 1,312 kilojoules for every 1 mole of electrons that were there. Of course, there's only 1 electron there, so we got to do a little bit of math. But we're just going to talk about it in those units because they're convenient. When this electron moves from one energy level to the next, we call it a quantum leap. And in order to do this quantum leap, it has to absorb energy and move to a higher orbit. So what it has to do is it has to absorb a photon of light or a quantum of light, a certain amount of energy. It doesn't have to be visible light. It could be electromagnetic radiation like radio waves or X-rays or gamma rays too. It just depends on how far it wants to jump. The lower the energy, the smaller the jump. The higher the energy, the bigger the jump. Okay. Here comes our little bit of energy here, and notice that the electron is going to move up as it absorbs that energy. Notice the energy hasn't disappeared, it's just helped the electron to get up into a higher energy level. Okay. The amount of energy that it just absorbed is easily calculated. You take the amount of energy that it had in the first energy level, subtract it from the amount of energy needed to be in the second energy level, and you find out that it needs 984 kilojoules per mole of energy in order to get up to the second energy level. That's a lot of energy. An electron can also fall down. When it falls down, it has to lose energy. Okay, that energy must be lost in order to move to a lower orbit. And so what the electron does is it loses the energy. It gives off a photon of light. Again, this doesn't have to be visible light. It could be any of the electromagnetic spectra. It could be gamma, could be X-rays, could be radio waves or microwaves. But it's going to give off that amount of energy and fall down to whatever energy level it wants to below it. Now, the amount that it falls has to be equal to the amount of energy that it loses. So in this particular case, the electron must lose 984 kilojoules per mole in order to fall down to the first energy level. You can see my math there to back that up. All right, the second postulate of Bohr. He must explain why atoms are gaining and losing energy. Electrons can gain energy by absorbing a photon. Electrons can lose energy by emitting a photon.
Right, because they're moving from different levels of energy.
As they move from different levels, and that's called a quantum leap. All right, so electrons must gain or lose energy in quantized amounts. Therefore, they have different colors of photons. And he proposes that this is a good equation to calculate the difference in energy.
Well, yeah, that would make sense.
That makes sense, right? You're trying to find the difference in energy, so you
The little triangle means difference in, right?
you calculate the final
Minus
energy and minus the initial energy, and you get the difference in energy.
It's basically the difference between the two levels.
Yeah, a third grader could have done that
Yeah,
one.
okay.
Okay. So, a quick summary. Bohr's got what is sometimes referred to as a ladder analogy.
All right, if I tilt my head
to
sideways,
the
yeah,
atom.
okay.
Okay.
I like
So, the atom has rungs that are orbits.
very specific rungs for each atom.
Just like your feet, the electrons can only exist on a rung,
Okay,
on an orbital.
all right.
Okay, so they can't be anywhere in between. Each energy level or orbital has a different amount of energy.
All right, we just calculated a bunch.
The higher you climb on a ladder, the more energy you have.
Right, the further away from the nucleus you are,
Right.
further away from the ground you are.
Okay, electrons must be in an energy level, which we just said. All right, electrons do not give off energy well in a given level. So if you're standing on a rung,
Yeah, you're not moving.
you're not moving. You're not giving off any energy. Okay. The electrons can move between energy levels, so they can take what's called a quantum leap.
Okay, moving up, they got to gain. Coming down, they got to lose.
Moving up, they got to gain energy somehow. Coming down,
Okay.
they're going to lose energy.
All
yeah.
right.
And the electrons give off photons when falling to a lower energy level. They need to gain when moving higher.
Ah, we just said that.
Okay,
How
yeah,
about that?
exactly.
We're so smart.
Okay, so that's a summary of what the Bohr model says.
Okay.
All right.